In week 1, Dan talked to you about basins and energy. Remember that gradient-like systems like to flow downhill. So what does this hill mean? For a passive mechanical system, this hill could just be the total mechanical energy of the system, which doesn't increase but decreases because of friction or other actuated control inputs. Here I've drawn a cartoon of what a hill might look like. So the actual state of the system is down below on the plane, and the hill signifies how the states kind of roll downhill. The basin is the rim of the funnel, which is all the states that are kind of funneled through into the goal location. But what if now we had multiple funnels? So instead of just rolling down one, we could have the states roll down one funnel, then into a second one, and then into a third one, etc. This simple cartoon is really the idea behind sequential composition, or back-chaining basins. The only rule, really, is that the goal location of the first funnel has to be within the basin of the second funnel. That's it. It's very simple and intuitive, but it's been used a lot in robotics. Here's an example of a juggling robot where this idea was used to transition between bouncing the ball and palming the ball to make it stop. This is not the only use of sequential composition. Way back in 1984, a famous paper by Lozano Perez, Mason, and Taylor described how sequential composition might be used to automate factory floor tasks. This is a peg and hole assembly task where, for instance, in the center right image, a successful assembly might entail moving the peg down, sliding it across to the left, and then down into the hole. This strategy, it'll be obvious to you, doesn't work for the center image, for instance. So what we're really doing is composing a sequence of maneuvers for the peg that ensure that the assembly will proceed correctly. Another assembly-like example is this one, where what we're trying to do is go to a known final configuration for these hex keys. The actuated control input here is the actuation of the tray underneath the hex keys, and so by tilting the tray through a sequence of maneuvers, we can channel or funnel the hex key through different configurations into a desired final one. This is also work by Matt Mason. This is a more modern example where optimization and robust control ideas have come in. What the researchers are doing is online motion planning. That is, they're selecting appropriate funnels prepared by the current state of this glider online, and using that to control it through unknown obstacles. Instead of executing control objectives sequentially, if we were to execute them in parallel, that idea is called parallel composition. There's going to be a lot more about this in section 4.2, but here's a quick recap of the origin and history. So let's say we build on the juggle that I showed you 2 slides ago. What if we wanted to now juggle 2 balls instead of 1? So this is really a parallel composition of the same controller, but there's an interesting twist on this. If you think about the ball-paddle state space, there's a big obstacle if the 2 balls are falling simultaneously because the paddle can't hit both balls at the same time. So what we're really doing is composing the 2 controllers, but avoiding the obstacle of the phase of the 2 balls being aligned. Another example is Raybert's planar hopper, which Jeff talked to you about last week. What Raybert did is he thought about the vertical hopping control and the forward speed control and the pitch control separately and played them all out together. There are no similar obstacles in this situation, but that's an interesting thing to keep in mind. To summarize, robot control can be thought of as flowing downhill on artificial energy functions. Sequential composition formalizes a sequence of tasks using back-chaining of basins. We can sequence coarse manipulation or assembly tasks, and there have been several other examples in the literature that I haven't had time to cover. Parallel composition describes satisfying multiple control objectives at the same time. What we have to keep in mind with parallel composition is that there are obstacles introduced into the state space that might not have been there without the composition. And secondly, we have to keep in mind that lots of systems inject coupling forces that would have to either be canceled or thought about appropriately. We're going to talk a lot more about parallel composition in the next segment.